All right, I guess we'll get started. So this week we're going to divert from programming and get into some RF filters. One of the things that you need to always be aware of is part of the FCC regulations that apply to us as amateur operators is that we are required by regulation to always have a clean signal. And that means that we need to use RF filters to make sure our signal doesn't, broadcast across multiple bands via harmonics. So we're going to actually go through. Now let me start the presentation here, and so we're going to actually talk about.
Hello.
Hi, what are you doing?
I'm doing my class.
Oh, I'm sorry.
Oh, okay. All right. So our goals for this this session is what is an RF filter. We're going to talk about the basic principles of RF filters, the basic types of RF filters, and then we're going to go into designing RF filters, and we'll talk about some design tools for RF filters. And then I'm also going to cover a document that I loaded up to groups.io, which is the GQRP's W3NQN filter data sheet. And what it is basically a all-in-one cheat sheet for the various different filters that you need for the different bands. So what they've done is, again, standing on the backs of giants. Now the GQRP data club has actually put together just a reference saying, okay, if you're doing this band, here's the type of filter that you need to get to suppress through, I think, second harmonics. So let's get started off with what is an RF filter. So an RF filter is basically an RLC circuit. That means resistive, inductive, and capacitance circuit that separates some frequencies from others within mixed frequency signals. So what it can do is this circuit can actually block stuff below a certain frequency, block stuff above a frequency. You can design it to only let a certain portion of or a band through, or you can block out a portion of the band. So we're going to use it to block out unwanted signals above where we're transmitting at. So we're going to be mainly looking for what we're doing low pass filters, but these are some examples of different home-brewed filters. This one, the first one was made with air wound core. This one's made with toroids. And here's another one that's using capacitors that you can adjust to trim it. We're going to be building something similar, but we're actually going to be doing it at the surface level, so we won't be using adjustable capacitors. We'll be using fixed capacitors based off of the data sheet. And the reason we want to have a filter is because whenever you generate a signal, there's always harmonics at frequencies higher above. And in this picture here, the tallest signal is actually the signal that we're our desired signal. But if you notice everything to the right, you see a bunch of other signals that are spaced out at equal intervals. And what we want to do is we want to degrade those so that they do not interfere with the other bands. And I think some of us saw that when we were playing around with the 5351 on Saturday during the build, and I brought up the full sweep of the spectrum analyzer, and you could see your signal at the max, and then you'd see a bunch of other signals out with it, and those were the harmonics that were being generated. So we're gonna basically want to clean those up. And what we're trying to do is drop them at least 3 dBs below whatever we're putting out. So the basic, how this actually works is the resonance between an inductor in frequency and a capacitor in frequency. If you think about it, with a capacitor, no matter what the value of a capacitor or inductance is, there's a frequency, and we'll go through the functions. There's a frequency that it will pass through all of the power applied to it, or the signal applied to it. If it's below that frequency or above that frequency, it will tend to degrade that signal by order of dB. When we're building filters, we're always looking for like a 3 dB or greater drop in the signal. And that's just to block out the unwanted signals. In this picture here, you see XC equals XL, and that's the resonant frequency, and that's where the maximum of your power is going to go through. Before that, in the lower frequencies, if you have a capacitor in a circuit with an inductor, the capacitor will tend to block the signal until it reaches the resonant frequency, and then it will start to let the signal go through. And as it gets closer and closer to the frequency, some of that power will go through, but it'll be degraded. And that's based on the mechanics of how a capacitor works. It charges the plate, and then when the power is removed from the capacitor, then it discharges. But we also use capacitors to block like DC noise and other low frequency noise in circuits, using that same principle. When we're talking about filters, we're going to use it to block lower bands until we get, or lower frequencies until we get to our desired frequency. With an inductor, it acts the opposite. At the lower frequency, it acts as a short, and until the frequency gets closer and closer to resonance, it'll continue to conduct the signal. Once it starts to go beyond the resonant frequency, then it actually tends to start increasing the impedance, which will then start to degrade the output of the signal and will start to block the signal. So that's kind of how the two work together in conjunction. Does anybody have any questions? Okay, we'll move on. So if you want to calculate let's say you got an inductor of a known value and a capacitance of a known value, you can say, well, if I put these in a resonant circuit, what frequency will that be resonant at? And so, and promise me, you guys are, I promise you will not be doing any math. This is just some background, so that you understand where all the calculations and all that come from. But if you take 2 pi times the square root of the inductance times the capacitance and divide that into 1, you'll actually get the resonant frequency. And this is actually, you'd say, okay, I have let's say a 360 microfarad capacitor, and I want to figure out what inductor I need to build. Well, then we could take this formula and refactor it, and based on the capacitance, we would basically take 2 times our resonant frequency and the capacitance that we have, and then we find out what type of inductance we need to build, or inductor we need to build with what inductance. If we had a known inductance value and we needed to know what type of capacitor, then we can use 1 divided by 2 pi at the resonant frequency squared times the inductance. And we're going to look at some resources that takes all the math out for you and says, here's what you need to do. But this is just to give you some background of how they did it before us. So, and then basically the impedance, whether we're talking about capacitive impedance or inductance impedance, if they're in, if you think about it, You get minimum impedance at a resonant frequency if you have a series resonant circuit where your capacitor and your inductor are in series together. You can get maximum if you create a parallel circuit with the capacitance and the inductance. So if you want, and you'll see from the designs we're going to be doing, it's kind of a mash of these with both series inductance or a series resonance circuits and a parallel resonance circuit for the filters we're going to be building. So what's all this mean? Well, basically we use series RLC circuits to pass frequencies. We use parallel RLC circuits to block frequencies. And the input energy at the resonant frequency passed through the filter is to the output when we're at resonant frequency. When we're not at resonant frequency, that energy is reflected back to the input as an impedance mismatch. So let's talk about the different types of filters. The most common one that we're going to be working on is a low-pass filter. And what it does is it passes frequency below a specified cutoff frequency. And then as you see in the graph here, it actually, as it gets beyond that frequency, which I think is right around 3 megahertz, let's say, it starts to degrade the signal. And the higher the frequency, the more and more it degrades it, impedes it. The other type is a high-pass filter, where what we're going to do is we're going to pass frequency above the specified cutoff frequency. Now let me go back a little bit here. So in this case here, the frequencies below about 5 megahertz are actually impeded or suppressed. And then once we get around 5, we're letting everything through. Really, you'd say this is probably a 4 megahertz filter because usually we're looking at 3 dB. Anything above 3 dB is considered being passed through. And then if we take a high-pass filter and a low-pass filter, if we were to put them together in a configuration, we get what we call a bandpass filter. And so what it does is it blocks frequencies below the band, the band cutoff, the low end of the cutoff, and then it blocks them above the high end of the cutoff frequency. So in this case here, we're talking somewhere around 3.3 to about 3.8 would be passed through. Everything else would be degraded. And then we have a band stop filter, and what it's designed to do, a lot of people would call it a notch filter, because what it does is it blocks everything in between the low and the high cutoff frequencies. Any questions about the different type of filters? You guys are quiet tonight. Okay, so there's common designs. There's the Butterworth. It's designed to basically, during the pass band, give you the flattest pass band signal. And it's used when you're looking for smooth varying phase response. Is important because you don't want to distort your signal. And then we have the Chebyshev, and it actually has ripples of equal amplitude that occur during the pass band, but it has a much steeper cutoff. And there's also an elliptical, and there's also a Kuhler, which we won't be talking about. Most of what you'll find, and a lot of people just use, are either Butterworth or Chebyshev, unless you're really into doing high-end filters in that. Then you might actually use a Quaylar or an elliptical. And these are examples of what the response curves look like. You see with the Butterworth, which is in the upper left-hand corner, the output is pretty much flat and steady, and then it starts to drop off. And then with the Chebyshev Type 1, you see that it's kind of got ripples in it, and then it drops off, and then it's flat. And then the Type 2, it's a little bit, it's nice and flat, but then after the drop off, you start seeing the waves in it. And then an elliptical, it kind of has a small ripple in it, and as it gets closer and closer, then you get more distortion at the cutoff frequency, and then it has a steep drop as well. So let's talk about the basic design of filters. And we'll start off with the simplest low-pass filter that we could build, and that's either in our circuit to put in either an inductor or a capacitor. That's the simplest low-pass filter we could do. And what that will do is, based on the value, it's going to filter out frequencies above our resonant frequency. Now, when we get into the next one, which is a simple high-pass filter, well, actually, I think this is actually a more complex. So these are considered higher order low-pass filters, and that's based on the number of poles that we have. So based on the number of components, we have a third order, we have a fourth order, and then we've got like a fifth order. And that's basically building in, if you actually think of it, we have a serial resonant circuit and then a second serial resonant circuit on the third order. Then we've got two, but it's kind of like a parallel. They kind of build serial to parallel, serial to parallel. And what we can do is, if for a high pass, we can make changes in our low pass filter and turn it into a high pass filter by taking and replacing it with a capacitor. So if we have an inductor and let's say our resonant frequency is, we'll say, 3000 megahertz, and we can replace the inductor that we have that is resonant at that frequency with a capacitor that is resonant at that frequency, and now we get a high pass filter. Or if we're using a capacitor for our low pass filter, we can actually replace it with an inductor that is resonant at our cutoff frequency and turn it into an inductive high pass filter. And here's examples of higher order high pass filters, where now if you saw before, our inductors, the capacitors were going from the signal to the ground, so they were shunting off the signal when we reached our cutoff frequency. Now we have inductors that are actually shunting between the signal and ground. So what it tends to do is allow that signal to go through, or actually it doesn't allow the signal to go through until the inductor actually reaches resonance, and then it starts to degrade the signal and stop it. So that's kind of how it works between the two. So here are just some simple steps. Let's say that we know that we've got a low pass filter and we want to convert it to a bandpass filter. So what we actually need to do, remember, with a bandpass, we need to build a parallel resonant circuit at the lower cutoff frequency, and then another parallel resonant circuit at the high cutoff frequency, in order to block the signals below our cutoff frequency and block them above our higher cutoff frequency. So what we would take is we'd take our low pass filter, and then we would go in and actually add or build a parallel circuit that would basically degrade the signals below our lower cutoff and then degrade the signals above our high cutoff. and then we would add another capacitor in series with the inductor that's between those two circuits, in order to allow just our resonant bandpass. Now we can also take, if we have a high pass filter, we can make changes to it to create a band stop filter. And what we're going to do is where our two capacitors are, is we're going to build two parallel resonant circuits to allow the band to go through below our low cutoff frequency and allow the signal to go through above our high cutoff frequency. And then we'll have another resonant circuit that basically blocks, a series circuit. So by adding in our inductors, then we're basically creating those the blockage, or the two filters to pass things through. So, any questions? Okay, and this is just, I took this straight from the ARRL handbook, and this is just the progression of filter design. If you're wanting to build a bandpass filter, you start out with a low pass filter, and then you add in the necessary inductors and capacitors to build the bandpass filter, to do your low end and your high end. If you're wanting to do a high pass filter, you can take the low pass filter and change it by swapping out the capacitors for inductors and the inductors for capacitors, and you'll get your high pass filter at that resonant frequency. And then once you have a high pass filter, you can then build out your resonant circuits for your band stop filter. So I'm going to go through a couple of design examples. So the ARRL handbook contains an entire chapter of tables and templates to design any type of filter for any given family, the order, and whatever performance characters you're looking at. It's a really good reference. But there's a lot of math involved. So what they've done is they've put together a set of normalized tables that are based on a low-pass filter with a bandwidth of 1 radian per second with 1 ohm input termination impedance. And then you can look those up to figure out what values you need for your inductors and your capacitors. And it's basically a normalized performing circuit. We'll go through one example. The steps are: you determine the type of filter you're gonna want to make. You determine your performance requirements, and then you select a family and order. Like, I want to do a 5th order Butterworth, and then you find the normalized values table for that family and order, and you pull out your normalized value tables, and then you perform the calculations based on the templates, and voila, you get your component values. So here's an example with a Butterworth high pass design. So it's going to do a Butterworth high pass filter with a 3 dB cutoff frequency at 250 hertz, and the system impedance is going to be 600 ohms. And so if you were wanting to do let's say a 3rd or a 4th normal, you would use these values in the equations that they have in the template, like 0.765 or 1.848. And then you'd plug those into the equations in the template, and I'll switch over to the template here. So this is the template. So, and see where they say G1, G2, G3, G4. And your resistance would be what your load resistance is that you want. So that would be, if you wanted 50 ohms, your R would be 50. If you wanted a 600 load or 600 ohm or 400 ohm, then you would use 400 for R. And you'd use the values that were in the previous table to derive it.
Hey,
A
Jim,
lot of work. Yes, sir.
just a quick question. So on the impedance, the system impedance, what's driving that in our application here for this project? Is that being
Normally
driven
that
off?
happen. That's normally been driven off of either, let's say, a mixer or an amplifier. So you might have your amplifier might have a different impedance, and you need to drop it down to like 50 ohms, or
Depends
it
on what you
normally
want to
has to
match
deal
the
with.
network to.
Yes.
So,
So
radios are typically 50. A ladder line system, different antennas, might be 400 ohms. The ladder line is typically 400 ohms, things like that. That's why you'd want to match your impedance, or you have to have a balun in there to match it.
In our case, though, we're not talking about the output of a amplifier or transmitter going into an antenna. We're talking about this little module, processor module, and clock system. Is that do we know the impedance of?
yeah, that's at 50 ohms.
Oh, it is. Okay.
Yeah. So we would design it at 50 ohms.
Okay.
But like Roger said, depending on what you're trying to match the filter to, because they actually, filters are used in more than just for RF output. If you think about it, filters are used to, on your input side. Also during your mixing, you'll have an intermittent filter there. Normally they'll use a crystal filter whenever you're trying to filter your intermittent frequency before you do your final mixing in that to make it as clean. But
Okay, that's where I was coming from was that piece of it. I thought we were trying with these with the signal that we're producing out of this. I thought we were trying that this was further upstream in the radio processing the front end of it than the output end. We were trying to filter here to get it clean before we start to use this for some other things. Okay, got it.
No, and in our case, this is going to be, we're going to make output filter. So this will be just before it attaches to the antenna.
Okay, that makes sense then. Okay, thank you.
Bill McNichols has a question.
Yes, go ahead, Bill.
Well, in the parts list, we have capacitors and resistors, but no inductors. So I'm probably the only person that doesn't know this, but how do we create the inductance?
Well, we're going to use toroids and magnetic wire to create that. And what I was going to do is I've got a bunch of them. I was going to make a mass order of what we need to build these, so that we'll just make one order and then give them out to everybody at the build session. But and I have tons of magnetic wire too. So I was thinking I've got plenty of that to cover everybody that's going to be building stuff. So that's why they weren't in the list.
Okay, I was just missing something. Thank you.
Yeah. Okay. Oh, actually, I wanted to. Well, I'll show you on this next one. Now, this one here, they're going to do a Chebyshev bandpass filter. So they're going to do a third order with like a 0.2 dB passband ripple with an input termination of 75 ohms, and the center frequency is going to be right at 4 megahertz. And you're going to have about a 1 megahertz ripple in the bandwidth. So what we would take is we'd take G1, G2, and G3 out of this table, and then we would go to the template, which is going to come up here in just a second, and we would plug in everywhere it says G1 and G2. and then 75 ohms for our resistance. So as you can see on A is the template, B is the actual results. So we would use for this one that we got a 75 ohm load, we'd use a 607 nanofarad inductor, a 2604 picofarad capacitor, and so on. And I don't know if you guys noticed this, but if you look, the values are the same on the two parallel circuits. And you'll see that with a lot of what we're doing is one order circuit has got a similar set of values as another order of the circuit. So like when we get into the data sheet and we walk through that, you'll see where like capacitor 3 and capacitor 5 has the same value, and capacitor 1 and capacitor 7 has the same value. So here's some design tips if you're going to do this on your own. It's simpler to use ELSI, which is a Windows-based program. It's a little bit more complicated, or a web-based filter design program, because you basically put in, this is my load, and this is my center frequency, and this is how much bandwidth I want, and it'll pop out what you need. But the family type and the order of a filter can be important when you're thinking about it, because the family type determines your frequency curve characteristics, whether you're going to have ripple in it. And the higher order you go, the steeper your cutoff's going to be. So if we were wanting to do, we've been talking about a project where we would build a bandpass filter where we could take the Morse code portion of a band and separate that, make a filter for that portion and a portion for the sideband side of a band. So we'd probably want a higher order filter so that we get a steeper cutoff, so that we don't interfere with somebody that's working on CW versus somebody that's doing sideband on the same band. Yeah, Roger, go ahead.
So you'll notice some of those values that Jim had calculated earlier were theoretical based on a particular center frequency for resonance. Most inductors and capacitors don't come in, those, 0.985, values. They come in like 1, 2.2, 4.7, microhenries, or 470, 680 nanohenries and things like that. So you want to choose an obtainable value of a part, and then calculate your capacitor value using that particular inductor, and then choose the closest capacitor to that you can get. So most capacitors are 5%. So a lot of your things, your frequency of resonance is going to be plus or minus a few percent, kind of thing like that.
Right. Well, and another thing is that you can't really use just standard capacitors for this. Normally you want to use MP0 capacitors or mica capacitors for RF, so that they've got a much smaller tolerance, and they basically, at frequency, their capacitance will be what they're rated, or what they say they are. One of the things a lot of people don't know, and I learned this from Mike Chittenden when we were a couple years back when we were doing some filter builds, that if you use just a regular capacitor, like a regular ceramic capacitor, it will, they're actually measured and valued at 100 hertz. Well, if you're wanting to use that at 4 megahertz, it might actually have a totally different capacitance. So that's why they always say you should use mica or MP0s, because those are actually rated to maintain their capacitance across the frequency band. And then actually, just as Roger was saying, once you get your calculation, you say, okay, I have this capacitor, right? Then go back and recalculate your inductors based off of that value you have for the resonant frequency using the equations we were looking at earlier before. And you also have to think about where your filter is going to live. If it's going to live behind a QRP radio, you can get away with like 100 volt DC ceramic capacitors. But if it's going to sit behind a 1500 watt amplifier, you're going to need much more, bigger capacitors that'll handle more voltage. Because, and same, as far as what's going on with it. And then, go ahead.
Yeah, so I was thinking from a surface mount part standpoint for the inductors. I'm sorry, for the capacitors. So if we're going to wrap our own inductors, you can theoretically wrap, close to whatever you need. So yeah, in that case, you'd want to choose your capacitor first, and then calculate your inductor, and then how many wraps you need. What your toroid width is, and all that kind of stuff. So.
Yeah. Well, and actually, I'm going to show you a cheat sheet that does it for us. So let me. Can you all see this GQRP club data sheet?
Yeah.
Okay. So this 2-page data sheet, and it's actually up in the files section, actually does all that work for us for a low-pass filter. So these are they're second harmonic. They're based off of W3NQN's article that he published in '99 on maximum second harmonic attenuation for filters in QEX. And so what we've got here is, I think, a 5th order filter. And what they've done is they said, okay, if you're going to build this is the circuit that you're going to build, this one up here. And then for each one of the bands, here are the values that you're going to use. So like we'll use 160. So your start frequency is going to be 1.8, and your cutoff frequency, well, that'll be your start frequency on it. So that's and then you can use for C1 and C7 a 1659. Well, that's not a standard value, so you could either use a 1450 and a 220 in parallel, or a 1500 and a 150 in parallel. That will get you the desired capacitance. And these are all standard values. So like for C3 and C5, it'd be a 2100 picofarad and a 470 picofarad, or it'd be a 2200 and a 330 picofarad. And then for C4, you'd either use a 378, which is not a standard value, so you would do a 330 plus a 47 picofarad capacitor. And then for your inductors, it'd be 5.21 and 4.7. And then they actually give you all the values for each of the bands, so that we'd want to build at. But they also say, okay, for your inductor wiring, you want to use this core, this toroid that has this T50-2 core or a T37-2 core, and you're going to do, like on the 160 for L2 and L6, you're going to do 33 turns on one, and then your L4 is going to be 31 turns. And it doesn't matter the gauge of your wire, but it'll basically be very close to what you're looking for if you use these values. Now there's other ones about if you're going to pass more than 100 watts through it, then you've got to step up to the next bigger one. But like a T37-2 is a pretty small, well, and a T37-6 is a pretty small toroid, where the T50s are a little bit bigger, because I think that's actually the, what is it? T50 is the circumference, I think, or the diameter. And I think that's in hundredths of an inch. So that's like 0.5, so it's a half inch, whereas the other one's like 0.37 inches wide. And then the -2 and the -6 is the material it's made out of. But this is actually up there. So, and we're going to use this when we actually start talking about next week when we start designing the filter boards. We're going to actually use these values and this circuit up here when we design our filter board. And what the intent is, we're going to design a board that we can plug directly into the breadboard, so that we can actually route the signal out of our SI5351 clock into this, and then from that, then we could take and we might even put a what do you want to call it? An SMA connector on the end of it, so that we can then go straight to an antenna. Now, I also have, I want to walk through and go over to the browser. So let me. So this is actually, and this is actually in the PDF. This is a very simple, if we wanted to do a low pass filter for, you can do like 3, 5, or 7 poles. So we'll do like 3 poles, and at 7.4 megahertz at our cutoff frequency. So everything above 7.4 would be blocked or would be degraded. And then our input impedance is 50 ohms. Can you guys see that okay, or do I need to make it bigger? Does that help? So we can then click on here and say compute parts. And then what it does is it actually gives you the circuit. And then if you're building it for like a Butterworth or a Chebyshev or a Bessel, you would use these different values. So if you have like medium to high impedance load, you would do a capacitive based kind of like pi network. But if you've got low impedance loads, then you would do 2 inductors with a capacitor that does the shunting to ground. And then they actually even give you an output. So if you look over here to the right, this is your loss. And as we go up in megahertz, you see as we get closer and closer to 7.4, we're down to 3 dB. And then as we go higher and higher in frequency, it drops off more and more. So this is actually dropping off as it goes to the right. It's higher in dB as we go to the right. And then this would be like a loss plot for a Chebyshev 3-pole. So we've got a little bit of ripple in here. That's where like we see a little bit of 0.1 at like 1.48 megahertz. And then so it does have a little bit of loss, but then it stays well above 3 dB. And 3 dB is the normal loss, is what we're always is what the FCC wants us to make sure that we suppress everything below 3 dB when we're trying to knock out harmonics and stuff. And then here's a plot for the Bessel. Again, you have a little bit of ripple in it, but if you notice, this is a more gradual cutoff compared to like the Chebyshev. It's got a little bit more dramatic drop in it. But as we get up here, right around 7.4, we hit 3 dB, and then it gradually just goes worse and worse. Now, if we wanted to design a bandpass filter, they also have a bandpass filter, and we'll do a 6-pole. here you can actually say, okay, what's my bandwidth? So I'm going to use a 50 kilohertz bandwidth, and we'll make the center frequency 7.050, which should be right smack dab in the middle of the CW portion of the band. And it'll be 50 kilohertz wide, so it'll be 25 kilohertz on either side. So this is the design for it, and your values. And then here's the circuit if you're going to do, if you needed a high impedance match, and the values you would use there. And then here is your loss plot. So as we're down here around 6.95, our loss is like 36 dBs, and when we get up to right around 7.27, we're above 3 dBs. So like right here, we go above 3 dBs, and then we're good until we get to like 707 down here. So this would be the higher end of your cutoff frequency, and then it drops back down and gets higher and higher. And then with the Chebyshev, it does it again, but you'll see that we do have some ripple in here right around the center frequency, where we're doing like 0.1 dB loss. And you got to remember, this is all theoretical. Once you're done with this, you're going to want to put it on like a spectrum analyzer, or to see what your actual loss is. And then here's the Bessel plot. So if you're sitting there saying, hey, I want to build me a bandpass filter for X, you can come out here and do that. Or if you're looking to do a low pass filter. Now they do also have high pass. And if we compute that, so that should pass everything above 7.4. And like here's your cutoff here. So 7.4 is where we're at the 3, and then everything above that is almost close to 0, but not really great. We can also do a band stop. If we go down here, I think we have a band stop here. And if we compute the parts, now the design's a little bit different, because now we have a series LC circuit and a parallel LC circuit, and then another series LC circuit on the output. And then here's where we've got two parallel LC circuits that tie into a series one for your high impedance loads. But see, here's your band stop where it starts calculations. Okay, so it's good, and then right around 7.25 is where we start dropping. And it isn't until we get above 7.75 where we go above 3 dB. So everything between 7.075 and 7.25 would be attenuated and brought down. Let's see what else. That was pretty much it. But if you go out here to the group, you'll find the data sheet here. There are also 3 really good articles by W3NQN that were in QST and QEX, and that are really good if you want to learn a little bit more. He doesn't go really deep into theory, but he does talk about why he selected values, why he picked this particular type that he was doing. But this is another one of those topics in amateur radio that there's several different ways to build a different, the same type of filter. It's why there's so many styles out there. And they all do something a little bit different, like we saw in the images from of the different types. Some have a much flatter pass band. Other ones have a little ripple in them with a steeper cutoff. But if you want to learn more about it, you can go there. The other place I would suggest that you go, let me go back over here and okay, so the first thing I would say, that first reference is that clean up your signals with Bandpass. That's the May-June 1998 QST PDF that I have out there. Chapter 2, Electrical Fundamentals, is going to tell you everything you ever wanted to know about capacitance and inductance from the molecular level all the way up to how it's used in design. And then Chapter 11, and now this is an older ARRL handbook. It may be the chapters may be a little bit different since the latest one that came out, but they do have a full chapter on RF and audio filtering, and they do get into very, very detail. And then if you have a copy of Experimental Methods in RF Design, they've got a ton of articles and material around building filters and discussion of why one is better than the other. If you're bored some night, you can always crack out the ARRL handbook and read through it, and you'll fall asleep within the first couple of pages, I guarantee you. And then the PDF does have links to LC. And then the web page that I was on for filters. I think that's actually it for tonight. Or right at, almost right at on the hour. So does anybody have any questions?
I don't, Jim. That was very, very good review. Thank you.
Well, and if you're studying for extra, this is on your extra test.
That was 6 years ago.
Yeah, same for me. Actually, this presentation I wrote, I think it was in 2015, and gave it to Lark back when I was studying for my extra. And I presented it at Lark one time, and when I started talking about the math, everybody's eyes went in the back of their head, because it's like nobody wants to be assaulted with math equations.
What spreadsheets are for?
Yep.
You can actually,
and I don't. Go ahead, Roger.
Excel has a great function called Solver, where you can set up, one equation for your L, your inductor, and one for your capacitor, and set a value, a goal in L, and have it solve for the most efficient C for our resonance. So it will, you give it a goal, and it'll sit there and iteratively solve the equation, even complex ones. So very useful.
Well, and also Roger,
for pointing out that the components are going to act different on the board than they do on paper. I remember undergraduate labs, like the calculation said it should be one thing, and then on the board you go, oh, okay, not quite.